Okay, guys, so today we're going to be doing thermodynamics and thermochemistry. So, sorry if you guys can't hear my voice very well. I'm going to try to speak up, but I'm outside, so there's a bit of noise. Anyways, so we're going to get right into thermochemistry. So, just before we get into some of the calculations and what is enthalpy and stuff like that, let's talk about what consists a thermochemical equation. What are we talking about? We have two things that are in the universe. Right, the universe is everything in what we're looking for, so the surroundings plus the system. The system is what the work is being done on, right? So it's the part of interest. What are we focusing on, right? So if we heat up water, is water the system, or is the vapor that's coming off of it, right? And then the surroundings, so literally everything else, okay? Now, there's three types of systems, right? First system we're going to be talking about is open system. So what is an open system? Where matter and heat can escape or come into the system, right? So this is an open system. This is me right now, right? If I drink something hot and then blow hot air out, it'll go out, right? Or if I spit something out of my mouth, the matter will come out, right? A little bit of an example, but that's okay. The second example is going to be closed system, right? So the only difference between a closed and open system is the matter cannot escape out, right? So heat can escape out. So if we were to have, let's say we're gonna be melting or not melting, but heating up a ball of any medium that is not a black body, it will give off some heat, right? It'll get hot, and through this being a closed system, the ball itself won't leave the system, but it'll release heat to its surroundings. Then we have an isolated system, which in theory is possible, but I personally have never seen an example of this, where not heat or matter can escape. So anything that happens in the system stays in the system and nothing else. So now we're going to be looking at energy. Thermochemistry is very, very related to energy and stuff like that, and how we measure it, it's always the difference, right? Represented by delta. So energy of the final minus energy of the initial. This is a... Sorry, I think the headphones disconnected. Okay, so here we can see how the energy difference is calculated. So if we want to calculate the energy of this universe, right, we do the energy of the final minus the energy of the initial, right? Now, what does this mean? If the energy of the the energy difference, okay, is either greater or smaller than zero, if it is greater than zero, then what does that mean? That means it's being absorbed. It's positive, right? Energy is being absorbed by the system. But if it is negative, then that means energy is being released in the system. We talked about this with exothermic and endothermic. So if the energy is positive, that is endothermic. If it is negative, it is exothermic. And this is shown by this, right? Okay, now we're getting into a little bit of calculations. This is the internal energy of the system, this is heat, and this is work. What does this mean? This, we know what it means and what it tells us. However, this we have to know about. It's not always positive or negative, but it's what happens in the system. So, for example, we have a liquid going to a gas. This would have a positive heat value. Why? Because it has to gain heat to become a gas. And vice versa. If we do a gas becoming a liquid, this would have to be negative because it is exothermic, right? And the work done on the system works the exact same. Is there being work done on the system, or is the system the one doing the work? Right, so we have to understand what positive and negative mean. So again, right before I go on, if it is positive, it means that it's being done on the system. The heat is being gained by the system. Okay, we always look at it in a point of view of the system. Now, the same goes for the opposite. If it is negative, the work is being done on the surroundings. The heat is being done on the surroundings, right? So, positive here means that it is endothermic, negative means that it is exothermic, and that is pretty much it, right? So there's three laws we have to memorize. This is the first law. Everyone's probably familiar with this, but I'm just going to repeat it. So what we have is the law of conservation of energy. So what does that mean? Energy cannot be created or destroyed. That means there's a set amount of energy in the earth, for example, or in the universe, right? But we're just transferring it in different ways where sometimes it seems as if one particular system has a higher energy, a lower energy, but in total, we always have a certain amount of energy that cannot be created or destroyed. Now, how can, remember this equation, E equals Q plus W. This W can actually be calculated by the difference of P times V. What is P? Pressure. What is V? Volume. So, just quickly understanding this, if there's no difference in pressure, okay, so that means it's zero, then work is going to be zero. If there's no volume, then that also means zero, right? Here there's an example saying calculate the work in kilojoules done during a reaction in which volume expands from 12 to 14.5 against an external pressure of 5 atmospheric pressure. So the 5 is our P, and 12 and 14, we find the difference. So we do 14.5 minus 12, right? To find the difference of V. And then we multiply, and that is what we get, right? We might have to go from atmospheric pressure to kilojoules. That's just some basic conversions, right? And I think I made a mistake here when I said delta P times V. It's actually P times delta V, okay? So now we're going on to another example. So a gas expands from 0.5 liters to 2.5 liters against an external pressure of 0 atmospheres. How much work is done? So what does work equal? We said work equals P times delta V. If delta V is 0, right? Sorry, if P is 0, what does that mean? No matter what the difference is here, it will be 0, because any number times something that is 0 will be 0, right? So always 0. Okay. How much work is done for the external pressure is 1. So what you do is you find the difference between these two numbers, which is 2. And then you do 2 times 1, right? But what is the difference here? We're in atmospheres, okay? So instead of work being in atmospheres, we have to actually change this to joules, which you have to go from pascals times 10 to the negative 3 meters cubed to then give us negative 200 joules. These are some basic conversions that will be on your calculator. You don't need to memorize. Maybe we'll have a class on showing how to do that. Now, for the following reactions, find the work. So this is a very good example, A, B, and C. So I'm going to give you guys a second to figure that out. All right, okay, so as we see in A, don't look at the elements. We're going to be going from gas to solid. What does that mean? If we have a gas, how do we make it a solid? We have to exert heat, right? We have to make these particles slow down. So what does that mean? That is exothermic. And how does that work? If we have particles like this, okay, in a really, really big container, it'll be a gas. But if you decrease the volume / increase the pressure and have this, then all those particles have to be so close together, becoming a solid, right? So the difference in volume is decreased, work is done on the system, right? As we can see here, this is the prime example of this. Now, we're going to be looking at the second question. Calcium carbonate gives you calcium oxide and carbon dioxide. Now, what does this mean? This is actually the difference. It is being expanded. Solid decomposes into a gas and another solid, right? So this W is negative, right? So instead of being a little tiny box like this, it becomes a big, big, big box where everything is spaced out and a little bit of solid, right? Now, what happens here? We see that there's Imagine molar coefficients like we did in equilibrium. 1, 1, 2. So 1 plus 1 plus 2 equals 2 over on this side. What does that mean? There's no difference and everything is a gas, so it is negligible. Okay, so there's no work being done. Okay, enthalpy and work are very similar in terms of their signs, right? So if work is being done on the system, okay, it's positive, right? So if we have negative Q, then we have positive W. If we have positive Q, then we have negative W, and so on, right? Okay, now we're going to be talking about enthalpy. What is enthalpy? I really don't like that word. It's a big word. It is heat. Okay, very, very simple. Now, what does enthalpy equal? Equals this guy, right? Heat, the difference in heat is enthalpy. So enthalpy equals energy plus PV. So energy plus Q, right? Sorry, E plus W equals Q. So it's really just this rephrased, but we're trying to find Q, okay? Now, heat change at constant pressure is equal to the delta H. What is this saying in this phrase? It means, you remember how to calculate work? It was P times delta V. If we're at constant pressure, and this stays the same, volume will stay the same because if pressure increases, then volume decreases, right? So it'll just be the simple value of Q. Okay? Now, here are some examples. I don't want you guys to look over here. Okay, don't look, don't look, don't look, don't look. Okay, this is A, this is B, this is C. I want you guys to tell me if this will be negative, positive, or nothing, for example. So in the first equation, we have CH4 plus O2 gives CO2 plus H2O plus heat. Heat is a product. What does that mean? That means it is negative. That means there's work being done on the surroundings, right? Work in the system is already absorbed, done its thing, it's pushing it out, right? So now, the second way of doing this is stoichiometrically, right? You can look at there's 1, 1, 1, 1, okay? Then here it doesn't really work out. But if you look, for example, at an equation that had 2, 1, then for pressure, we know on which side it's going to occur for the Châteaubriand, right? But that's for a different lesson. Stoichiometric-wise, right, we see the same thing. This is still exothermic. And then this will be, what's it called? Endothermic. So what this slide is trying to say is in relation to Hess's law that we're going to get into, but it's saying that if everything is of 1 molar coefficient, this is the enthalpy. Since we know the enthalpy of formation of this entire thing, if we multiply it by a stoichiometric coefficient of 2, we have to multiply everything here by 2, right? And the direction. So if we switch the reactants and the products around, what does that happen? What happens is that you actually have to times the enthalpy value, right, by negative 1. So we go from negative 890 to positive 890. Now, what is Hess's law? This is a very good example. So Hess's law, imagine it's a big, big, big puzzle in thermochemistry, and it's very, very, very easy to solve, is that you solve for the enthalpy of formation, so the heat of making the chemical equation that you're looking for through a series of other reactions. How does it work? They'll give you one chemical equation that this is like what you're trying to find, right? Now, they'll give you a bunch of little ones with their enthalpy of formation values, and what you do is you try to cancel things out. So we see here there's CH4 plus O2 gives CH2O plus H2O. Now, is the side of the CH4 on the right side? Yes. Okay, we don't need to times anything by negative 1. Is it of the same molar coefficient? Yes. Okay, this is good. It stays the same. Right, so we're going to put, let me get a pen. So we're going to do negative 275.6 kilojoules plus the next thing, right? Because you have to add everything together. Then we see that is the CH 2, is it anywhere here? No, doesn't really matter for us. O2 is on the right side, yes. CO2 on the right side, yes. H2 on the right side, yes. Okay, so what do we do here? Are we going to multiply by 2? No. Why? There's already one O2 here, so these add up to the correct amount. Is CO2 good? CO2 is good too, so we're going to add this guy up as well. Okay, and then the last one is H2O liquid and H2O gas. We know that this is supposed to be on the other side, right? Because these two cancel out. So we have to multiply this guy by -1, so plus -44, and it's 2, so times 2, okay, plus, so, sorry, I did, okay, plus another -44, so whatever this equals when you add everything together will give you the enthalpy of formation of the first chemical equation that we're looking for, okay? This is the exact same thing, just showing you how to do it. Same thing here, okay? Do this for extra practice. I won't be going over it because it's the same thing. This is what it should look like. Okay, state functions. So they, a lot of the times they'll ask questions like, is this a state function? Is enthalpy a state function? Blah, blah, blah. Memorize these, but understand them as well. So a state function is any given mathematical function, right, for thermochem that depends only on the state, not how it got there. Okay, so what does that mean? I have a car. Okay, I'm driving a car. I'm going to France. Okay? At the end of the destination, the end destination is France. It doesn't matter if it took 2 days or if I walk there or whatever. At the end of it, I got to France. So if someone asks me, where did you go for holiday? I'm going to say France. I'm not going to say by car by 2 days to France. I'm going to say France. So the end thing matters, and the end thing in state functions is the phase. So anything that's by the phase, okay? So imagine the phase is the destination, and that's a state function. It does not matter how it got there, right? So what is that? Internal energy, right? Because it's just the sum of the kinetic and potential energies of a system. Enthalpy, the heat change, right, is only dependent on the phase. Entropy, again, the phase is degree of disorder, and free energy is how much free energy is there, again, only on the phase. Now, standard state, this is just a big fancy word for saying if they do not give you any values regarding the conditions, what state is it in? What's the temperature? What's the pressure? Stuff like that. It is assumed at standard conditions to be at 25 degrees Celsius, which is 298 kelvins, and 1 atmospheric pressure. Okay, so you must know this and memorize this. Okay, that's all. Again, if a super zero is indicated, that the variable is at standard state. So if you ever see this little zero, that means it's at standard state. And just to add on, if you ever see a E with a little zero here, then what does that mean? That means it's initial. Okay, what is this? These are standard enthalpies of formation. These are things you can use to find the enthalpy of formation of a given chemical equation. How does that work? Or for Hess's law. But Hess's law, they usually give it differently. With this table, you're usually doing delta HF gives equals HF of products minus HF of reactants. Okay, so I'm going to show you guys a formula. I know my handwriting is a lot fast, but pretty much using these standard values, you can find the standard enthalpy of formation of a chemical equation. So let's do one. There you go, right here, right? So what is this? It's saying that the delta H of formation at standard is the enthalpy of formation of products minus delta H of reactants. Okay? And that's just how you calculate it. You just plug it in. It's very, very simple. For thermochem, almost everything we do, the difference is final minus initial, right? So products over reactants. So you can memorize that. Okay, here it's saying calculate, uh, here it's saying calculate the heat of reaction 4, CH4 plus 4F2, whatever. You're going to notice, and what I want to talk about is the 4F2 is not written here. Why is that? If you guys remember diatomic molecules like hydrogen, oxygen, fluorine, bromine, stuff like that, they are naturally in pairs, okay? So what that means is they naturally exist as a diatomic molecule. There's no formation needed for that. Okay, and another thing is you just have to multiply these by their molar coefficients, right? So we have 4HF here, the HF has to be multiplied by 4, and it is written right over here. Okay, so just for practice, you guys can put this in your calculator and understand how to use a calculator. This is the, what's it called? The formula, again, to understand the enthalpy of formation and standard conditions, and that's it. Okay. Which one of these, the combustion of 1 mole, so the combustion is the, imagine explosion, so the combustion of 1 mole methane, this is the reactants, okay, to give either of these two, okay. Now, one is CO2 gas and H2O liquid, or CO2 gas and H2O gas. What is being exothermic? So as we said, exothermic is being releasing heat, right? Giving off more and more and more heat. So it would be number 1. Why? Going from gas to liquid, you have to lose even more heat, right? So there's even more heat being lost here than here, right? And that is exactly why. So it's further condensation of H2O gas to H2O liquid being more exothermic. Now, this is another sample question. So the heat of formation of each of components involved in the dissolution of sodium chloride are given below. What is the heat dissolution of NaCl? What do? You add these minus these to give the answer. Okay, that's all it is. You guys remember HF products minus HF reactants gives HF of the final. Okay, entropy. This is where stuff gets kind of interesting. Imagine entropy as the one guy who gambles a lot, and that is pretty much why it's a thing. Entropy, the second law of thermodynamics, states that entropy always increases in the world. You could never have an actual decrease of entropy. Now, what is it? It's the degree of randomness. How random can it be? But some things will have a lower entropy than other things, right? As it transfers. Same way energy cannot be destroyed and stuff like that, or created, entropy always increases in the world, okay? The degree of randomness always gets more and more, right? How is this calculated? As I said, pretty much everything in thermochemistry is the difference, final minus initial. So final entropy minus initial entropy. And yeah, so higher disorder equates to increased entropy. Okay. Now, the third law of thermodynamics is, so what did I say? First law is law of conservation. You cannot create or destroy energy. Second law was the entropy of the world is always increasing. And the third law is at absolute zero. What is absolute zero? It's when, like, the temperature of absolute zero, so Kelvin zero, which is impossible to get to, okay? In theory, the entropy of a crystalline solid, of a pure substance, is zero, okay? This is just a law you kind of have to memorize. There's not much to show about it. It's just a theory of law of thermodynamics that you just have to know. Now, here is showing you how randomness works in different phases. As we know, solids are particles that are very, very, very closely packed together. As liquids, they become a little bit more random and less, like, more distance to each other. And gas, they are very, very random and distant to each other. So this here is less random. We know a solid isn't going to just go away. Gas is, though. So increase randomness between gas to liquid. All right. Uh, Again, this is just some examples. So solid to liquid, what happens? Entropy increases. Solid to gas, entropy increases. Liquid to gas increases. Other way around, entropy decreases. As temperature rises, right? As we go from solid to gas, for example, temperature rises, entropy increases as well. And the larger the atomic radii of an element, because it's bigger, the electrons have more of a probability to be in different quantum orbitals, especially for bonding and stuff like that, which increases the randomness or the degree of freedom, right? So that's why we see HF, which is super, super small, HCl, which is a little bit bigger, HBr, which is a little bit bigger, and HI, which is a lot bigger, right? We have increasing entropy. And another way of calculating it is molar coefficient. So as we said for the Le Chatelier's principle, the molar coefficients, when you add them together on each side, let me draw this out for you guys. So we have 2 and we have 1 here. This gives us 3. However, here we have 2. So difference of n equals 3 minus 2. What does that mean? That means we have more products than we do of reactants, okay? That means we're generating more particles, okay? Imagine we had 2 particles, now we have 3, okay? So what does this mean? Increasing entropy. Okay, so we're going to see this in terms of their actual values now. Predicting relative entropy, standard entropy values, the 0, the little super 0 over here. Let me just point to it so you guys not to forget. Okay, how do we see this? So as we see, this is just a visual. Temperature change. As we go from lower temperature to higher temperature, the entropy values increase. Phase change solid. The gas increases. Dissolution, right? So if a solid's dissoluting or a liquid or a gas, what happens? They increase, right? And the complexity of the element, as the atomic radii gets bigger, so does the entropy value and the randomness, okay? All right, so here it says place the following systems in order of increasing randomness. 1 mole of gas, 1 mole of solid, 1 mole of liquid. So we know it's going to be 1 mole of solid is the least in entropy, then it's going to be the liquid, then it's going to be the gas. Now, here's a question. It says, which of the following would exhibit the highest entropy value, right? So we have water at a certain temperature, certain temperature, certain temperature, certain temperature. Which was the highest temperature? It will be D, which is water at 100 degrees Celsius. Okay, predicting the sign. Here, what it is telling you is very simple. You have to look at the molecular randomness. So how many moles of each are present? So here we have 10, here we have 9. So entropy value would be positive here. Okay, here we have 1, here we have 2. So decrease, right? And that's pretty much it. So negative, positive. Here is just a practice for the exact same thing. Look at the molar coefficient, see if the products have a higher, then it's positive. If you have reactants negative, reactants moles is higher than negative, and stuff like that. Now, there's one thing I want to mention. If, for example, you're going 2 to 3, okay, that's positive, like large and positive number, right? Because if you were to do the 3 minus 2, you have a positive number. However, let's say you're going the other way, right? Large and negative. I just want to really make sure you guys understand this. Is if you're going, for example, NH3 and H2O, okay, 1 plus 1 equals 2. Now, here is 1 and 1 as well. But there's something that we can't do here with the molar coefficients. This is a gas becoming an aqueous solution, right? So phase change again. So here it decreases, right? So large and negative. Look at here. I want you to think to yourself without looking at this answer, okay? Why is this just a small entropy change? This is because there's 1 mole, and 2 moles. So 2 equals 2. So there's no difference in moles. There's no difference in phase. There's no difference in temperature that's told to us. So there's just a small change. Okay? Something for you to just know. If it's in a question, you have to know it. Okay. Using the absolute standard entropies at 25 degrees Celsius, find delta entropy for each of the following reactions. What do? I said, in thermochemistry, let's say I forgot about the entropy equation. What do? In my mind, I know almost everything in thermochem is products minus reactants, right? So, what I would do is, I would take 3 times this number, so I'd get 615, okay, minus 2 times this number, okay, and it'd give me this, and then the same thing for here, which would give me this, okay. Then you compare these two values. Whichever one has a greater value has a greater change in entropy. Okay, so what was the second law of thermodynamics? We said that the degree of randomness always increases. You cannot go down, but it can be transferred other places. If something else becomes a change of like a larger negative entropy, then something else is of higher entropy, right? So a way of calculating the entropy of the total is the system plus the surroundings, right? So we said, what is in the universe of a thermochemical equation? The universe consists of two parts, the part of interest, which is the system, and the surroundings, which is literally everything else, okay? Now, what does this mean? If the entropy value is above 0, okay, the reaction is spontaneous. Why? Because it is more favorable, okay? We said the world always increases entropy. It always gets weirder, more random, whatever, okay? So, as entropy increases, we're favoring the law and it works, okay? If we're going the other way, it's non-spontaneous. You have to put energy in, right? So, for example, I have a block of ice and the ice melts, becomes water. Okay? If I leave it out in normal standard temperatures at 25 degrees Celsius, this happens naturally, It's favorable, it's spontaneous, the entropy increases, everything is good. But if I have a liquid, it's not just going to freeze at 25 degrees Celsius, right? At standard conditions. Done deal. And if the entropy total equals equilibrium, what does that mean? Then equals 0 equals equilibrium. There's no net change. Now, again, as I said, entropy of the universe is always increasing. Okay, we're going to be getting into defining the free energy in terms of enthalpy and entropy. So, what is this? Gibbs free energy. It is a very simple way of understanding it is free energy, released energy, right? So the equation for this is delta G equals delta H minus temperature in kelvins times the difference in entropy, right? So these values will be given to you and you can calculate them, right? And moving on is the free energy is just the usable energy, and entropy is temperature times the difference in entropy. So this table is sometimes hard to memorize for students because they get mixed up, minus, positive, they don't even think about what it means. How to memorize? Very simple. If you have a negative delta H, which means negative heat, what is it? It is exothermic. If you have positive entropy, that is in favor of being spontaneous, right? So, what does that mean? It's spontaneous at all temperatures. Okay, it's always favorable. Now, let's say you have an exothermic reaction over here, and you also have something that's becoming more ordered. Okay, I'm gonna give you guys two examples for you to memorize this thing. Okay, so imagine ice freezing. Okay, ice may be water might freeze at a standard temperature somewhere that has low temperatures. Okay, it's spontaneous. Water freezes spontaneously at low temperatures. That's how you mine. Remember, minus, minus. Okay? Right here. Okay? Now, it is non-spontaneous for high temperatures. Then we move on to an endothermic reaction, okay, which means it absorbs heat with the decrease of entropy. What does that mean? No, it just means it is not spontaneous at any temperature. We cannot make it spontaneous. We need some type of activation energy. And the last one is an endothermic reaction that increases entropy. What does this mean? An endothermic reaction that increases disorder. For example, a liquid turning into a gas. Okay, let's say water evaporating. Water cannot evaporate at standard condition. It requires high temperatures. Okay, and that's that. And you can also think of it in terms of the chemical equation, as I said. Gibbs free energy equals T delta S minus delta H. So we need delta G, okay, to be negative, okay? If delta G is negative, then it is spontaneous. If it's positive, then it's non-spontaneous. So if we think about it mathematically, we need the T times entropy to outweigh the H. Okay? Sorry, other way around. My bad. Okay. This is just a little bit of practice for you guys, just understanding the water freezing thing. I think it's very simple. You guys got to use it for practice. This as well is very simple. Same here. Yep, this is also very, very easy. Okay, so delta G of a reaction, right? As I said, again, in thermochemistry, if you're confused, do products minus reactants. Most of the time you'll be right. This is it. They're going to give you standard values. You subtract, you add everything in the products, add everything in the reactants, then you subtract. Very, very simple. Now, if you get a positive value, okay, that means the reaction is non-spontaneous. But if this was negative 54 point whatever, it would be just spontaneous, okay? Okay, now, another way of calculating free energy under non-standard states is using RT, okay, times ln of Q. Q is the reaction quotient, T is temperature in kelvins, R is the Rydberg's constant, which is, I think, 0.8026, okay? And you use the initial, not initial, but you use the standard Gibbs free energy. Okay, what does this mean? If you remember reaction quotient, which is products over reactants, if it is smaller than, if it is smaller than 1, then what happens is there's more reactants than products. But when it is bigger than 1, then the reaction is mostly products. And we could think of it, again, I'm going to write it out, is because of the formula. Okay, another thing that you can think of is the RT ln Q. If it's smaller than 0, which means G is negative, this means that it's spontaneous and it goes in the forward reaction because of the Q value, and the opposite goes for right here. Alright, so beginning with pure reactants, the free energy decreases if the delta G is smaller than 0, right? What does that mean? It's spontaneous, moves to equilibrium. Okay. However, when we have pure products, the free energy also decreases as it moves to equilibrium. So this portion is not a spontaneous reaction. Okay. So, what is the relationship between the enthalpy and the entropy changes for a process at equilibrium, right? Boom. That's all it is. At equilibrium, you plug in 0 over here, and that's it. you get the equilibrium. Standard gives free, and that's all you get. Again, this is just a simple table showing you the relationships. Uh, Q is pretty much the reaction quotient, so if it's bigger or smaller, you see if it's bigger than 1, it's mainly products. If it's smaller than 1, it's mainly reactants. It's at equilibrium. Okay. You guys know this from equilibrium, right? Uh, this is a good practice for you guys, just to kind of get through it. Calculate the K. We know K from here. That's pretty much it. Q equals K. Remember that. And that's it. And this is the last slide I'm going to be talking about. So, remember, standard delta G, the Gibbs free energy, can be calculated all these ways. Okay. This way is extremely simple. I wouldn't even spend time on it. This way as well, don't spend time on it. These two, okay, I'm going to stop the screen so you guys can take a screenshot. I would do these questions just for extra practice. So, this one, I think it's very useful. And I think that's all you really need. Another thing to memorize was, again, the 3 laws of thermodynamics. So, energy cannot be created or destroyed, which is the law of conservation. Second, entropy always increases. And third, at absolute zero, entropy is 0. And that is it. So I hope you guys understood what thermochemistry is, or at least the basics of it. And if you have any questions, I think you can just comment them down below, and hopefully we'll check them and answer you guys. Okay, bye bye.